Hi everyone, in this talk I'm going to present a relatively simple caching strategy that can reduce noise in Monte Carlo PDE solvers such as walk-on spheres. Walk-on spheres and related techniques such as walk-on stars or the walk-on boundary method solve elliptic PDEs such as the Poisson equation, and crucially, like ray tracing, they can do so without any volumetric meshing or global solves. This makes them prime candidates for problems in visual and geometric computing because often we want to perform simulation or analysis on imperfect assets that were originally intended for design or visualization purposes, such as this example of a potential flow simulation in a wind tunnel. The only requirement is we need to be able to perform both ray intersections and closest point queries. This is great, but there's a catch. Since most Monte Carlo methods solve PDEs independently at every point in the domain, they end up taking a lot of long walks from each of these points. And since there's no sharing of information across walks, we end up with redundant computation, especially when we evaluate the solution densely over the entire domain. These solvers additionally suffer from noise that's typical of most Monte Carlo algorithms, and they don't exploit the high degree of spatial regularity that's found in solutions to elliptic PDEs. To overcome these challenges, our boundary value caching method instead takes walks only from the boundary and reuses the estimates from these walks over the entire domain. In our wind tunnel example, this results in significantly smoother streamlines. Reusing sample estimates is not a new idea and has in fact already been successfully applied to Monte Carlo rendering algorithms. For instance, methods like virtual point lights and Reister can dramatically reduce noise by sharing light paths between pixels. Our method specifically takes inspiration from virtual point light methods, which first deposit radiance estimates in the scene and then reuse these cached values to generate a radiance estimate at each pixel. To understand our method, let's first start by considering a Laplace equation with mixed Dirichlet and Neumann boundary conditions. The Dirichlet boundary conditions sets the value of the solution on the boundary, whereas the Neumann boundary condition specifies the value of the normal derivative of the solution. The boundary integral equation represents the solution at any point in the domain as an integral of the Dirichlet and Neumann values over the boundary. In this integral, G represents the free space Green's function, which is known analytically. What this integral really says is that if you know both the Dirichlet and the Neumann values on the boundary, you know the solution everywhere on the domain. Of course, even if we know the boundary values, we need to evaluate this integral to determine the solution at any point, and we can do so by constructing a Monte Carlo estimator. Now, we obviously don't know both types of boundary data, so we have to estimate them. Boundary samples that are on the Dirichlet part of the boundary can directly use the known Dirichlet values, but require estimation of the unknown Neumann values. Boundary samples that are on the Neumann part of the boundary can directly use the known Neumann values and require estimation of the unknown Dirichlet values. Before we discuss how to estimate these boundary values, notice that the kernels in the Monte Carlo estimator for the boundary integral are the only part of the expression that relies on the position of the evaluation point x. This means that both the sample points and the estimates of the boundary values can be reused across evaluation points. This key insight is what allows us to cache and reuse boundary values for all points in the domain. So how exactly do we go about estimating the boundary values? There are many pointwise estimators, such as walk-on stars and walk-on boundary, and each of these can be used to estimate the boundary values. Our method happens to use walk-on stars since it's unbiased, has bounded variance, and can efficiently handle mixed boundary problems. We run several walks for each boundary sample on the Neumann part of the boundary to estimate the complementary Dirichlet values. To estimate the Neumann values, we use a pointwise gradient estimation technique proposed by Sawhney and Crane that defines the gradient as an integral over a ball that's centered on the boundary sample point. This technique only works for points that are inside the domain, so we do have to slightly offset the point from the boundary, and in our paper we discuss how to choose this offset in more detail. Finally, all of the walks originate at points near the Dirichlet boundary, and so these random walks end up being relatively inexpensive. Altogether, our algorithm leverages pointwise solution and gradient estimates as follows. First, we uniformly sample a set of boundary points. We perform random walks at each of these boundary points using walk-on stars to estimate either the unknown Dirichlet or Neumann boundary values. Then we compute the kernels for each evaluation point and update a running estimate of the solution at each point. And then we simply repeat until convergence. Our algorithm is simple to implement, trivially parallelizable, and it's both progressive and unbiased. The sharing of walks between points that boundary value caching enables results in much smoother solution estimates in equal time when compared against pointwise estimators like walk-on stars, which have to compute the solution independently at every single point in the domain. Our method also immediately extends to spatial gradients of the PDE and uses the exact same boundary value estimates that we use to compute the solution. Again, our method has far less noise than pointwise methods like walk-on stars. Our method can additionally handle Poisson equations, which have an added source term. In this case, we generate an additional set of sample points that are inside the domain, and can directly evaluate the source term in each of these points without any need for additional random walks. Finally, simply reusing uniformly sampled cache points can result in artifacts near the boundary because the Green's function and Poisson kernel are weakly singular, and we don't importance sample them. Virtual point-like methods in rendering, as well as the boundary element method, also suffer from similar artifacts near the boundary. In our paper, we describe how to mitigate these artifacts by adapting ideas from virtual point-like methods. Now, compared to independent Monte Carlo estimates, our caching strategy improves runtime efficiency because we only need to perform random walks from the boundary, and we share these walks across all evaluation points. Reusing boundary samples also suppresses the salt and pepper noise found in most Monte Carlo algorithms because it introduces correlation into the solution estimates. In practice, this smoother solution profile is beneficial for visual tasks, such as harmonic interpolation of texture coordinates in a deformed cage, as shown here. Compared to classic approaches like boundary element method, we don't require a high-quality mesh of the volume or the boundary. So in this example, for instance, BEM suffers from large global errors without mesh refinement because of local aliasing of boundary data, and it can completely fail in domains with irregular elements. Our method, on the other hand, has no aliasing artifacts irrespective of tessellation quality. We additionally can focus computation on local regions of interest by estimating both the unknown Dirichlet and Neumann values on the boundary of a smaller subdomain. This is quite different from BEM because BEM has to perform a global solve over the entire boundary. One challenge of our method, however, is that error in our solution estimates is much more global, like traditional solvers. But our formulation is progressive and unbiased, so the error will vanish with more boundary samples. Finally, we found that stratification of samples leads to significantly better results. Just like in rendering, where generating stratified samples can massively improve image quality. Now, there are a number of ways in which our method can be improved. For instance, we'll benefit directly from any improvements to the walk-on stars algorithm because we rely heavily on it as a subroutine. Our results should have lower error with a more principled approach for estimating normal derivatives on the Dirichlet boundary. Evaluating the boundary integral equation inside the domain currently suffers from quadratic complexity, so incorporating techniques such as Barnes-Hutt and stochastic light cuts should significantly improve performance. It's also worth exploring how we can improve estimates from individual random walks by reusing information during the walk itself. And finally, it may be possible to develop a unified caching scheme that incorporates other recent variance reduction techniques, such as bidirectional walk-on spheres or mean value caching. It seems like there's still a lot of scope for reducing variance and sharing information across walks. Thanks for listening. You can find links to our paper and code in the description below.